All right, guys, welcome back. Ah, I hope you enjoyed your day off on Monday. You're probably busy studying for your AP exam. What was it? I think it was human geography. So I hope that went well, but we are back to geometry now. And I know this will be good news for a lot of you. We are up to our last circle theorem. So we've done a whole bunch of theorems involving angles, and then we moved on to the lengths of chords and tangents and secants, and now we are up to the last of them, right? We've done two tangents, we've done two secants, we've done two chords, and now we are up to a tangent and a secant, and we're going to find a relationship between their lengths when they are connected to an external point. So we've done a lab for all of our theorems so far, and this one will be no exception. So if you want, just read through this theorem and see if you can figure out what you should be constructing in your lab to see the relationships between this tangent and secant. So in your calculators, what you should be doing is making a circle and constructing a tangent, maybe something like that, and constructing a secant, and you are to find a relationship between the lengths. So I'll tell you what to measure. What you're going to be measuring is the length of the tangent. All right, from there to there. You're going to be measuring the entire length of the secant from there to there, and you'll be measuring the external portion of the secant. All right, so this should be looking really similar to our theorem involving two secants, right? We had two secants. We said, that was a while ago, but we said that the entire length, right, times the external portion is equal to this entire length times that secant's external portion. So we're doing the same thing. We're measuring the entire length of the secant and its external segment as well. And well, with a tangent, we don't really have two parts, do we? We only have the length of this tangent, so we're going to be measuring just that piece. All right, so if you haven't already, go ahead and draw this in your calculators and see if you can figure out the relationship. All right, so I will be doing this on Sketchpad. So let me hop on over to that and actually make a new sketch. All right, so for this lab, we've got a circle, we got a tangent. So what do we need to make first to construct a tangent? All right, we need either a radius or a diameter. And that is because, I have to, sorry, I gotta restart Sketchpad because I'm on the trial version. Well, let's me work on it for 20 minutes and time expired. So let me redo that real quick. All right. So like I was saying, got a circle, and to make a tangent, we need a radius or a diameter because we know tangents are perpendicular to the radii or diameter of a circle. So I'll be clicking the radius and that point and constructing a perpendicular line. So hopefully you did that as well in your calculators. And now here is a secant. And they meet up at this external point there. Behind this. And let me just draw it in this piece of the tangent because that's really all I need. So I asked you to measure the length of the entire secant as 14.58. Measure the length of the external portion. That's 8.57, and measure the length of the tangent. All right, so when we did two secants, the relationship was length of entire secant times the external portion. So let's multiply these two numbers again, see what happens. Calculate that times that, and that is about 125. And well, we only got one thing to measure here for this tangent, so let's try multiplying this by itself. And let's see what happens. So number, calculate this times itself. And will you look at that, we got the same result, 124.95. And of course, I can move any of these points around. Actually, moving this point around doesn't even change the value of dB. You can adjust B as well, though. And take a look. Those are always equivalent. And we're going to use this to write out our theorem. So let's go back to the iPad. Boom, over here. And before we write it out in words, let's write it out using a little equation. So we saw that this tangent, let's call this a B. Right, so we saw that AB times itself, in other words, AB squared was equal to the length of the entire secant. So let's call this BCD. So the length of the entire secant is DB times its external portion, which is CB. All right, so that is the relationship when you draw a tangent and a secant to a circle from an external point. So let's write this out. For our theorem, we're going to be writing it out a little differently than what you might expect. We're going to say if a tangent and secant are drawn to a circle from an external point, then the length of the tangent is the mean proportional. There's a word you haven't seen in a while, right? You guys remember the synonym for mean proportional? Probably do not, but we could have also written the geometric mean, right? But it's the mean proportional or geometric mean between the length of the secant and the length of the secant's external segment, right? Or the part outside of the circle. Secant's external segment. So what we are saying is that this tangent AB is the mean proportional between the length of the secant, which is DB, and its external segment, which is CB here. All right, so how does that make sense? Well, first of all, what is a mean proportional? We studied mean proportionals when we did Hills and SAS. So hopefully you remember, if you have a right triangle and you draw, or you drop an altitude, right? We make two similar right triangles. And what we saw was that this altitude was a mean proportional, right? SAS. Right, this altitude was the mean proportional between the two segments of the hypotenuse. So there was one of them. And so this A was the mean proportional or the geometric mean between those two segments of the hypotenuse. And we also had hills. And that's an Iser leg of the original triangle. Let's say this leg, right? That is the mean proportional between the entire hypotenuse, right? And this segment of the hypotenuse, which connects to that. So, which connects to the leg we're talking about. And so these legs are also mean proportionals, right? In this diagram, that leg's also mean proportional, and the altitude's a mean proportional between two different things. So in this scenario, we're saying that the tangent, which was AB, so let's put AB over here and AB over there, that was the mean proportional between the entire secant, which was DB, and its external portion, which is CB. So that means we can set up this proportion, and you'll notice if we cross multiply, boom, boom, right, we're gonna get what we showed on the calculator. So that tangent is the mean proportion. Pretty cool. So we showed it on a calculator. Before we can use this theorem on a test or anything else, we need to prove it. So let's do Euclidean proof. I gave you the givens, so we're going to be changing up the letters a little bit, but it'll be exactly the same. Setup, we got a circle. PS is tangent to the circle O. So let me draw a tangent line, let's say over here. It's tangent. right? That's tangent PS, and it intersects secant PQR at P. So let me draw in a secant. Let's say this guy is our secant, and that's going to be PQR. So again, we're trying to prove tangent squared, or tangent times itself, equals the entire secant times its external portion. In other words, that tangent is the mean proportional between the secant and its external segment. So how are we going to prove this? Well, it's the same analysis that we just did before. If PS is the mean proportional, then can't we say that PR over PS equals PS over PQ? Right, so if I look along the top, I see the letters P, R, and S. So that's probably one of the triangles, right, that we're going to have to construct. Right, because obviously to prove this, right, we know we're going to be using CSSTP. So we got to prove two triangles similar. So if I look along the denominator, I see PS and Q. So that is my other triangle, PSQ right there. So if I can prove this big triangle similar to the smaller triangle, well, I will have enough information to set this up and therefore prove that PS is the mean proportional between PR and PQ. Or we can show that. So let's just analyze this proof a little bit first. I think the obvious one is that they have this angle P in common, right? And then we just need to find one more angle in common. So this should not be too bad, right? We've talked a lot about intercepted arcs. Think about which arc we're going to be using. Aha. That arc SQ, right? It's intercepted by this angle PSQ, right? And it's also intercepted by this angle SRQ. And in both cases, those angles are going to be half the measure of the intercepted arc based on theorems that we have previously proven. So here's the breakdown of the proof. Let's write this out. I'll be writing just the steps. You guys can write the reasons. But first step, of course, is write out your givens. And the reason is given. All right, step 2. All right, sorry, it's getting a little loud. I'm going to pause the video and I'll be right back. All right, guys, hopefully it's not too noisy, but where were we? All right, so givens are done. Next, we have to construct RS and SQ, right? Because that was not in our original diagram. So step 2, construct chords. It's still pretty loud, but construct chords RS and SQ. And SQ, right? Between any 2 points, only one line segment can be drawn. Step 3, let's go with the easy one first. Angle P is congruent to angle P, reflexive property. All right, step 4. All right, here is the good one. Well, we need to prove another pair of angles congruent. So we can show that angle is congruent to this angle. So I'm going to say that the measure of angle R is equal to 1/2 the measure of the arc it intercepts, which is arc SQ. Right, and the reason for that is this angle R here, right, it's an inscribed angle. So the reason will be the measure of an inscribed angle is equal to 1/2 the measure of the arc that it intercepts. And now we can say also that the measure of angle PSQ, that's also going to be 1/2 the measure of arc SQ. Right? And the reason for that is we showed that when you have a tangent and a secant, the angle formed by a tangent and secant is equal to 1/2 the measure of its intercepted arc. Right? Again, the angle formed by a tangent and secant is equal to 1/2 the measure of the intercepted arc. So here we go. Now we can do a substitution. Step 6, measure of angle R is equal to the measure of angle PSQ. Step 7, we can say they're congruent because angles that are equal in measure are also congruent. Step 8, our triangles are now similar by angle. So we gotta name our triangles carefully. Big triangle, I will name that as, start with PRS. So triangle PRS is similar to triangle. Well, P is going to correspond with P in the small triangle. So P. Next, I went to R, which is where I have that congruent symbol. So I will go to S next. So PSQ. And those triangles are similar by angle. Next, I can copy and paste this. Now I can say that this proportion is true because of CSSTP. Corresponding sides of similar triangles are in proportion. And lastly, if I cross multiply, I get PS times PS, or PS squared, equals PR times PQ. And that is product of the means equals product of the extremes, right? And again, here are our means, right? That is the mean proportional. So O equal palm. And hooray, we have proven our last circle theorem. I have another sheet that's posted with this, with these notes that goes over all of the theorems in one place. So that's definitely a good, I guess, like a study guide or like a cheat sheet, you can call it. But that has all the circle theorems in one place. And so let's do one example with this. This is not too bad. It's just like how we would use any other theorem. But using the picture above, if RQ is 9, let me copy this diagram. If RQ is 9 and PS is 16, find the length of the external segment of the secant in the simplest radical form. So go ahead, pause the video, try this. This should be something you are capable of doing at this point. And let's take a look. RQ is 9 and PS is 16. And we're looking for the length of the external segment of the secant, which would be QP. So let's call that X. So the formula says that, or the theorem says that this tangent is the mean proportional. So I can say 16 squared equals, it's a mean proportional between the entire secant, which will have a length of 9 plus X, right? The entire thing, RQ, times its external portion, which would be just X. So solving for this, we get 256 equals, distribute that X, X squared plus 9X. Let's move that 256 over to the other side. And, I don't think I picked the best numbers here. I'm sorry. I don't think anything multiplies to 256 and adds to 9. Let me double check though. All right, sorry. Gonna make this change in your notes, but let's make PS 24. I would not give you something that crazy. So this length, that should be 24 instead. Right, this diagram is not drawn to scale whatsoever. If I did want to draw it correctly, maybe it might look something more like this, so that SQ would have a length of 9. That looks a lot better, right? But anyway, so instead of 16 squared, we're going to have, all right, hold up. All right, I messed that up a second time. What I meant to say is that I want RQ to have a length of 24. So I'm sorry about this, but if I made RQ 24, right, PS is still 16. Also looks a little more to scale on my diagram. But now let's try solving with these numbers. All right, again, I apologize. But 16 squared would equal 24 plus X times X, right? So the entire length of the secant, 24 plus X, right, times the external portion X. And I get 256 equals, once I distribute, I get 24X plus X squared, or X squared plus 24X. All right, minus 256 on both sides. And This here, I think, is factorable. 8 and 32 multiplied to negative 256, so I can factor this to x plus 32, and x minus 8 equals 0, right? You would just list out all the factors of 256. It is a pretty big one, so I'm just going to go in order. 1 and 256, 2 and 128, 4 and 64, 8 and 32, and also 16 and 16, right? But that pair of numbers can make 24. So it's going to be positive 32 and negative 8. So I can meet the signs here. And solving for this, I get x is equal to 8, or x is equal to negative 32. Right? Do not automatically reject the negative because it could make sense. But in this case, it doesn't make sense because we can't have a negative length. But if this were like x plus 64 or something, negative 32 could be a perfectly viable answer for x, right? But not in this instance. We have to reject, which means x is equal to 8. What were we looking for? We were looking for the length of the external segment of the secant. So we really are just looking for x, right? Make sure you read the question. I could have asked you to find the length of the secant, in which case it would be 24 plus x, or 24 plus 8. But only the external portion, so QP is equal to 8. Right, and that's it. That is how you use the theorem. And that is our last one. So let's take a look at this circle theorems review sheet real quick. There's just a tiny bit that I want to add, right? But it gives you the general rule in words. The measure of the central angle is equal to the measure of the intercepted arc. And they give you using the diagram. So this is very nice. We have all our theorems here. We got central angle inscribed, 2 chords, 2 secants, tangent and secant, right? And down here we have the lengths. So 2 intersecting chords, right? It's the product of those segments formed by the 2 intersecting chords are equal to each other. Right, got tangent and secant, chord and diameter. What did I want to add onto the sheet? Oh yeah, that's right. I wanted to add over here for 2 tangents, right? We also know if we have 2 tangents drawn to one circle that these 2 tangents, they would be congruent to each other. So we can also add that onto here, that AP would be also congruent to BP, right? And again, that angle, half the measure of these 2 intercepted arcs, just like if we had 2 secants or a tangent and a secant, same rule for all 3, right? And only for tangents, right? We also know that this angle and the measure of that arc are going to be supplementary. I think that's down here, right? Yes, angle P is supplementary to arc AB. So hopefully you are keeping a track or a list of all these theorems, but now we also have it over here. So let me know if you have any questions about any of these. I do probably want to do like another quiz, just all on circle theorems, but we got a little bit left of circles, even though we're done with all the theorems. And that's going to be it for today. Again, hope your APs went well. Take care, stay safe, guys, and I'll see you guys next time.